Hi everyone, my name is Gruosso and today I will present to you our work, Solid and Effective Upper Limb Segmentation in Egocentric Vision. After a brief introduction and related work, I will discuss the construction of our dataset and the proposed approach. I will show you some of our results, and finally I will summarize conclusion and future work. Recently, deep learning powered web solutions have been increasingly developed, and several immersive frameworks were designed that allow users to perform network inference and training directly in the browser. In this example, I train a small network for digits and written classification. On the right, you can see the plots for monitoring the loss and accuracy during training. And at the end of the training, I test my network in the browser. In this example, I collect a dataset consisting of different images, several images showing rock, paper and scissor for image classification. I design a convolutional network and train it in the browser. And at the end of the training, I test my network using images captured using a webcam. This is an example of face landmark detection using a deep network and perform inference in the browser. This is my last example and shows end tracking in the browser. The most common web applications are online virtual reality chat rooms that allow users to see each other and share contents. This is an example in the figure that shows Mozilla Hub's environment. Users are usually represented with a virtual avatar. Another example is a 3D collaboration platform on the right, where the users can interact with the virtual object using their controllers that are also visualized in the virtual scene. Web-based solution can provide a virtual environment that runs directly in the browser, and so results in an easy setup and cross-platform portability. With the widespread availability of wearable RGB cameras and hand-mounted displays, systems for analyzing and detecting ants in a first-person perspective called egocentric vision or egocentric viewpoint have been designed. In this figure, you can see user ants tracked using a lip motion controller and visualized in the virtual scene using a virtual ant. The question is, can the user be more involved in the virtual reality and web-based virtual environments, seeing their real ants and limbs in the virtual scene? We designed and proposed a deep learning approach for upper limb segmentation in an egocentric vision. It can allow locating the user limbs interactively and obtain accurate information at pixel level. That may increase the user's sense of presence and body ownership, for example, in Web 3D virtual environments, providing a general-purpose solution that can be executed on any device using a web browser and without a specific hardware configuration or software installation. In these images are shows on the first line the inputs, and on the last line our segmentation output overlaid on the input images. There are several works on hand and arm segmentation. The most part of them focused on hands up to the wrist or bare arm. One of the first focused on left and right and identification and segmentation. And the most recent was proposed by Gonzalez et al. They train a deep neural network for hand and arm segmentation. That network was trained using their own semi-synthetic egocentric arm dataset that consists of more than 10,000 composited images. Although their model achieved really interesting results, several false positive and segmentation errors in color similarities between background and foreground were found. Since obtaining ground truth segmentation mask is very labor-intensive, time-consuming and sometimes impractical, synthetic and semi-synthetic datasets were proposed, have been widely collected, and they allowed to get labels quickly and with little effort. As you can see on the left, synthetic ants are produced in a completely artificial manner, and often they look unrealistic. And semi-synthetic dataset combines real and computer-generated components. Both approximate real data. In the case on the right, semi-synthetic data were obtained from the EgoArm dataset, and we found several errors in the foreground that was extracting using a green screen. As you can see, often the ants looks green due to foreground extraction from the green screen setup, and different images were used as background. Often they are low resolution, and the composited images look really unrealistic and artificial. Often several computer vision techniques are needed to bring realism to those data, and for this reason we focused on real dataset, analyzing existing datasets such as this data, and we found some errors in the annotations in this case, or polygonal masks. In the case of Ego YouTube ants, we found only labels for the ants up to the wrist, and since we were interested in ants and arms, we discarded this data. In other cases, only bare arms were labeled and clothes were not labeled, and there were some errors in the annotations and so on. So we collected a large dataset, real dataset, that overcomes the limitation of existing dataset. In the case of Web 3D and deep learning approaches, recently some works were proposed. In particular, the first two introduced models for model shape estimation, and the last one proposed a conditional generative adversarial network (GAN) for global illumination maps generation of 3D human organs. They used TensorFlow.js for network prediction in the browser, which is a deep learning frameworks that allow network training and prediction in the browser. Our dataset consists of about 46,000 well-labeled real-life images. That includes the best data from a DSH and TIGO dataset. We investigated the quality of this data to select the best data of both images and labels, discarded the worst data, such as with errors in labels. We selected images in egocentric vision with different skin tone, as you can see, different tones, different lighting conditions, scenarios, in the case of motion blur, occlusions with object and with interend occlusion. And we collected our dataset called EgoCam that allows increasing the number of data in our dataset, introducing also female limbs with different clothes, and capturing also the elbow and the upper arms, because existing dataset focused only on hands and the first part of the arm. But in the case you use a camera with a wider field of view, this camera captures also elbow and the upper arm. So since the collected dataset had different orientation and aspect ratio, we designed an automatic procedure for square cropping. At the end of the cropping, we inspected all the saved images and deleted the useless clipping, such as with no hands or no arms. The proposed approach is based on convolutional neural networks that are feed-forward neural networks designed to process data in a multidimensional, provided as multidimensional arrays, such as images. The main advantage consists of a huge reduction in the amount of parameters and invariance to input translation compared to standard feed-forward fully connected networks. This kind of network is composed of a first part responsible for feature extraction from low-level to high-level features such as line, edges, and then objects such as recognizing the tail or the mouth. And the last part of the network is built with fully connected layers, and in this case performs classification. Contrary to a common feed-forward neural networks, as shown on the left, where each neurons in a layer is connected to all neurons in the subsequent layers, CNN neurons are arranged in 3 dimensions with height and depth. The core block is the convolutional layers, which perform convolutions, where each neuron is connected only to a local region in the input spatially, but to the full depth. Each hidden neuron share the same weights and bias on its connection, and for this reason all neurons in the first hidden layer, convolutional layer, can detect the same feature but in different location of the input image. The convolution is performed between 2 volumes, the input volume and the convolutional kernel, which consists of 1 or more filters, and the values of those filters is learned automatically during training. Although it is essential to specify some hyperparameters such as the filter size or the stride, which is hyperparameters that control the moving of the filters on the image. Another type of convolution is called authors or dilated convolution, which upsample convolutional filters with holes, defining a spacing between the values in the kernel controlled by an hyperparameter called authors rate. In this example, a 3x3 kernel is dilated with a rate of 2. The goal is to obtain a wider field of view that takes the context more into account, but without increasing the computational cost and the number of parameters. This is really useful in the case of real-time segmentation. Since convolution are linear operation, usually a nonlinear activation function is used after convolution. The ReLU is the most used nonlinear activation that allows a faster and effective training of deep networks on large and complex datasets. It is efficient, especially in image-related tasks. After convolution, usually is placed a pooling layer, which performs pooling operations such as max pooling or average pooling, which is applied to each feature map independently, contrary to convolution, and performs downsampling along the spatial dimensions, with a huge reduction in the number of parameters and ensuring translation invariance. We designed a deep learning approach based on the DeepLab v3 Plus architecture, which is a deep CNN with an encoder-decoder structure. The encoder extracts semantic information and reduces the size of the feature map, while the decoder recovers spatial dimensions and detailed object boundary information. We trained different networks, changing the backbone network. In particular, we test ResNet with 50 layers, 101 layers, exception with 41 and 61 layers respectively. The encoder is composed of a backbone network, an ASPP module, a one-time-one convolution or point-wise convolution, while the decoder performs bilinear upsampling and convolution to upsample the feature map. The heterospatial pyramid pooling module allows capturing the multi-scale context effectively and improve segmentation. It consists of several layers in parallel, a convolution, a point-wise convolution, 3 authors convolution, and an image pooling. We train our models using a GPU, performing the augmentation. We use the cross-entropy loss function, which is a well-known loss function for segmentation tasks, and SGDM, stochastic gradient descent optimization algorithm, with a polynomial learning rate with the power value 0.9 and momentum 0.9. All networks using pre-training weights. The first 3 cases, ImageNet, which is a large-scale dataset for image classification and object detection. The last one, pre-training weight on ImageNet and the Coco dataset. Coco dataset is a smaller dataset, but used also for segmentation. We performed a first test using our test set, a quantitative comparison using well-known metrics shown in percentage, accuracy, intersection over union, and mean F1 score. In the case of the overall evaluation, we performed an average over classes, and in the case of classes, we used accuracy, intersection over union, and mean F1 score. The obtained values show excellent results for all training networks. The worst model diverges by a limited quantity, 1 or 2%, respect to the best model. So we spec'd the mask obtained, and we noted that several small errors can be found. And in conclusion, it was not so easy to identify the best network observing those results on our test set. Then we performed another test using Egogesture-Seg, which is a subset of the well-known Egogesture dataset, which was labeled by Gonzalez et al. It consists of challenging scenarios and situations, and we conducted this experiment to assess the generalization level and highlight the differences between the performances of the training models. As you can see, the best model was the last one with exception 65 backbone network, and there is a significant difference compared to the other models. Then we performed a qualitative analysis. Those are some of the images of Egogesture-Seg dataset and the output obtained. As you can see, the network with exception 65 backbone found the limbs in all images with only minor errors in the third case. And it was the only model that did not make classification error related to the background in the last image. Okay, these are really challenging with strong lighting, dark limbs, and a huge amount of motion blur. In our opinion, the results obtained with the Egogesture-Seg dataset prove that using initial weights pre-training on both ImageNet and Coco dataset can help the network to have a broader view and be able to generalize better in this case. And furthermore, the conducted tests show that the exception-based architecture is more robust to challenging situations than the ResNet one. We compute the average inference time using the GPU and testing our RGB images, and all models prove more than real-time performances. Those are some results on videos which were obtained using the best model, exception 65 as backbone network. The colored segmentation output masks were overlaid on the input frames. This is a really challenging situation in which you can see a watch with the reflective surface, and in this case a small reflective metal ring on the user end and on the user finger. There are also some errors, but impressive results were achieved in all these cases, also in the case of cloth. In conclusion, we proposed a robust deep learning approach for upper limb segmentation from an egocentric vision in unconstrained real-life environments. Our network proved to be robust to both bare and clothed human upper limbs. We obtained good results and promising results in the case of inter-end and end-to-object occlusion, in the case of variable lighting condition, skin colors, indoor and outdoor real-life environments. We collected a large comprehensive dataset to train our network and tested several configurations to find the best model for this task. It could allow users to see their own limbs in the virtual 3D virtual environments, and interact with virtual objects using their own hands instead of virtual avatar, improving the user sense of presence and embodiment in virtual environments, and providing a general purpose solution that can be executed on any device using a web browser. In the future, we plan to conduct a user study to assess the usefulness of our approach in web-based immersive application and perform a comparison with state-of-the-art methods for egocentric and ARM segmentation. Thank you for your attention.